Alright, so in this tutorial we are going to look at the theory behind the law of conservation of momentum. From the lab yesterday, we saw that within a decent percent difference, that for the various collisions that we looked at, that the amount of momentum before the collision, looking at total now for both cars, is equal to the total momentum after the collision. So we want to understand why this happens for any given interaction. Okay, so we're going to do a very general derivation. It's pretty easy to follow, and this is a derivation that you're expected to be able to reproduce or understand various parts of. Okay, and then we'll do some practice with it, and then later on you'll have your own time to do it in class. Okay, so the theory behind this is in many interactions, the magnitude of the impact force and time are very often very difficult to determine. Thus, we need a way to predict what happens to objects after a collision, all right, even though we have no information about what happened during the collision. So we're going to basically look at collisions where we don't have the impulse information that we got from the computer when we had a collision with a force sensor, because that's very, very impractical. So we want to get around that and still be able to understand what's going to happen after collision. And it's pretty straightforward. So what we do know, so we're going to look at, I'm sorry, before we do that, we're going to look at any general collision between objects A and B. So A could bump into B, they could hit head on, they could stick together, they could separate. Everything we did in class and beyond is what we can look at. And so if we're going to look at two objects, and this by the way applies for multiple objects, but we'll start with two in one line, and eventually we'll have to understand it in two dimensions. Let's say we have A collides with B. Okay, so what happens when A collides with B? Well, we know that they feel a force. We don't know how much force, but that's beside the point. What we do know is that A feels a force of F, and B must feel a force of negative F. Okay, so that's the third law, and that's really the key to the law of conservation of momentum. More than anything, it's that. Everything that follows stems from the fact that when the two objects collide, doesn't matter what the situation, if one feels a force F, the other one feels a negative F. Now, not only do they feel force, they feel it for a certain time. How much time? T. And this is going to feel it for the same time, T. Okay? So what's going to be the same for them? Well, a combination of force and time, of course, is an impulse. So they're going to feel, if this feels an impulse of J, B is going to feel an impulse of negative J. Okay, so the same magnitude, opposite direction. Well, why do we care that they felt the same impulse or an impulse? Well, the consequence is going to be a change in momentum. So this is going to get a change in momentum. I'm going to put a positive in front of that, and that's got to equal a negative change in momentum. So now let's interpret that, because this is really what we're after right here. You don't have to circle this on your notes. I'm just circling the highlight. What we're saying is for any collision, the gain in momentum of one object equals the loss in momentum of the other object. Okay, so a positive delta P means gain in momentum, and negative delta P means a loss of momentum. Or another way to put the total change in momentum, if I look at the sum of all that, is zero. Okay, that's nothing more than a conservation law. Now, when we presented in class, we didn't look at it so much in terms of changes, but again, the change in one is equal to the negative change in the other, or the overall change 0. For any collision, I'm sorry, let me write that down, my bad. Gain in momentum of one object equals the loss in momentum of the other. Okay, or put another way, total momentum before a collision equals the total momentum after. So really the problem to look at is just keeping track of momenta of one or two objects before and after, taking into account vector issues, and it's fairly straightforward. Now again, this holds for all collisions, for all objects, in all situations, as long as there are no external forces. This is a really important caveat. All right, so in our lab, we didn't get perfect momentum because A, our measurements weren't perfect, B, I was introducing external forces. One of them could be my hand when I was triggering the car. The other could have been from the earth, the friction between them. So if we neglect those, if we define our system as just the cars, then anything external to that, if they exert a force, will change the momentum of the system. So we'll have to discuss in class this idea of a system and how it relates to conservation of momentum. but we'll do that later. Okay, so mathematically, how do we write this? Very simple. The simplest way of writing conservation momentum is we say the total, that's sigma, momentum before, just P, equals total momentum after. And we use prime or an apostrophe to indicate after. Okay, now this expands, all right? This is a very compact equation. So what that becomes is, if I have two objects, I would say P of A, the first object, plus the momentum of B must equal the momentum of A after, so I put a prime, plus the momentum of B after. So when we talk about conservation momentum, we must discuss at least two objects. There's no rule that says the momentum of one object stays the same after collision. The total must stay the same. And then we can expand this even more. We could call this MA times VA plus MB times VB, all right, equals, usually the masses don't change, but we have a different velocity after, plus MB VB after. So this is where it gets to be kind of a pain, because we essentially have 6 variables in this equation. We have the 2 mass variables and we have 4 velocity variables. So in the problems we're going to start now, we're going to be given 5 of those 6. But it's just an issue of keeping track. So let's do some quick little problems. We'll start with very general ones and then we'll move to more specific ones. Okay, so I have some generic objects here, A and B, that you're given information about their momenta and the direction they're moving. And we have before and we have after. What we want to be able to do right over here is we want to be able to predict the momentum of the unknown, namely B prime, and then later on we want to predict how fast they're going to be moving. Okay, so we'll do that together and then we'll move on to more complicated problems. All right, so we have situation 1A, we have A with a momentum of 6, B with a momentum of 3, they're both moving to the right. And then afterwards we have A is moving with a momentum of 4, so it lost some momentum, and so what is the momentum of B, and what direction is it? Okay, again, there's 2 ways you can approach it. We can talk about the loss of one equals a gain in the other, or we can look at total. So I'm going to look at total. So I have right here, sigma P prime, to help me keep track. So the total momentum before is 6 plus 3. All right, that's easy, 9. So what's going to be my total momentum of both of them after? Well, by the law of conservation of momentum, it's going to be 9 as well. Not negative 9, but 9. So if this is 4 for A, then plus this has to equal 9, then it would stand to reason that momentum of B is going to be 5. And since it's positive, we're going to put an arrow here, and it's still moving to the right. So look at this problem again, just make sure you follow it. It's pretty straightforward math. Things will get more complicated. Okay, so how about situation B? So what's different here is a head-on collision, so we have positive and negative momentum. So in this case, it's 9 plus a negative 3, so our total is positive 6. Therefore, our total after must be positive 6. That's got to equal this guy, which is negative 6, because it's 6 to the left, plus this guy. So negative 6 plus what equals positive 6? I believe this would have to be a momentum of 12, and implied is to the right. Okay, which would make sense. They collide and one goes left, the other must go right. Total momentum stays the same. All right, in part C, I'll let you try on your own. The things are a little bit different. I give you, instead of total momentum, I give you individual masses and velocities. And the mass is going to be 10 here. The mass is still going to be 4 here, and then fill that in. So your goal is to try to find the velocity of the B object afterwards, okay? So take a second or two, try to work that out, and then I'll work out the answer. Okay, so breaking it down, we have a total momentum of 20 for this guy. We have a momentum of negative 8 for this guy, so the total is positive 12. The momentum of A afterwards is 10 times 1, 10, plus the momentum of B afterwards has to equal 12. So the total momentum, or the momentum of this guy, is going to be 2. So I got to do a lot of little thinking here. Therefore, if its mass is 4, then the velocity afterwards is going to be the total momentum, or the momentum of B, excuse me, divided by the mass of B, which would be 2 divided by 4. So this is going to be moving at half a meter per second to the right. Okay? So, again, this kind of problems we're going to be doing, just not as schematic. All right, let's see. We have 9 minutes, so let's try to do a few more here. Get as much practice in as we can. Okay, so we're going to look at three different types of situations: elastic collisions, inelastic collisions, and what are called explosions. Okay, I'm going to give you very crude definitions of them, but the formal definitions will come later. So an elastic collision, formal definition means that you have no loss of kinetic energy. Now that really doesn't mean anything to us. We haven't defined kinetic energy, but we will later. So the simplest way to look at elastic collisions, but you can't define it like this when you ask a test, is basically when the objects hit, they don't stick together. Okay, so let's say we have the following, and I'm going to draw a schematic for a 30 kilogram person right here that is moving east, so we'll call east this way, 5 meters per second. Okay, when she collides with another person moving west, who happens to have a mass of 15, is moving 6 meters per second. All right, so I have a very crude diagram to help me keep track of my information. And then afterwards, what do I know? After collision, the first person moves with a velocity, so it still has 30, moves to the east with 1 meter per second, and we want to know what's going on with the second person after. So I use this line to differentiate between before and after. Okay, so let's answer some questions. So what's the total momentum before the collision? All right, so we just have to add these both up. We should show work, but I'm going to do shortcuts here. So A is going to have a momentum. PA is going to be 30 times 5, or 150 units. I'm not going to put units here. And PB is going to be 15 times negative 6, negative 90. So the total would be positive 60 units of momentum. All right, next question. What's the total momentum after the collision? So if you look at the after part, we have 30 times 1 for the object A, but we have no information about B other than the mass is 15 kilograms. So we can't find the total momentum after by adding the 2 after. That defeats the purpose of the problem. We want to basically use the conservation momentum to figure out the velocity of this guy after. So how do we figure out the total momentum if we don't have the individual momentums after? Well, we use the law of conservation of momentum, which says sigma p prime, what we're looking for, equals sigma p, and we found sigma p earlier, so it's very simple, sigma for 60 kilogram meters per second. You need to write this equation here in order to justify that. All right, now that we know that the total is 60, we can now look at the two parts afterwards. So what's the momentum of person A after the collision? Pretty straightforward. That's PA prime is going to be the mass, 30 times 1. That's going to be 30 kilogram meters per second. Okay, so what's going to be the momentum of person B? Again, we can't do mv because we don't know the v prime, but we can use momentum. So we know that sigma p prime total equals pa prime plus pb prime. Okay, like in the very beginning, we took the two momenta, add them up to get the overall. Now we're going to use the overall, knowing it's 60, has to equal one of them, 30, plus the other. So it makes sense that pb prime is 30 kilogram meters per second. Okay. So both objects have the same momentum after. That's no law that says it has to happen. It's just more of a coincidence, all right? Now, what's the velocity of the second person after? Pretty straightforward. The velocity of the second person after, that's ultimately what we're after, is equal to the momentum after divided by the mass. So that's going to be 30 kilogram meters per second divided by the mass of 15 kilograms. I believe that's what mass was. That gives us 2 meters per second. And boom. We know how fast they must have been moving without knowledge of what went on during the collision. Now, you might say this is kind of cheating a little because in order to solve this, I had to give you one of the objects afterwards. And that's the best we can do right now. When we learn about energy and elastic collisions, we'll actually learn a way to get around having to have that second piece of information. In fact, just based on the initial information, we can predict what both will be doing after, which is kind of neat, but complicated. So just to verify we've done things right, let's calculate the change in momentum for both. Okay, so let's do change in momentum for A, which is PA prime minus PA, the final minus initial. So PA prime, if we go back and look, was 30 kilogram meters per second, and the initial was 150, so 30 minus 150 is negative 120. So it lost 120 kilogram meters per second. So the law of conservation of momentum tells us that B should have gained 120, and let's check that out. So delta PB would be PB prime minus PB. That's going to equal, let's see, PB prime was 30, the initial was negative 90, 30 minus negative 90 equals positive 120. And So sure enough, we see momentum is conserved. Okay, we'll take a look at the other situations in class. Hopefully this makes sense.